So in the last lecture, we finished discussing the design of FIR filters, and in the remaining time that we have left for this class, I want to briefly touch upon the IIR filters, although in today's world we often don't use them because of their non-linear phase characteristics, but it's important for you to still be aware of some of the properties in case you do end up using them. So as we had talked about quite a few lectures ago, the only IIR filters that we can implement are the ones that are given by constant coefficient difference equations. So implementable forms are given by constant coefficient difference equations, which are typically written as, for example, you'll see them written, let's say, d0 yn minus d1 y of n minus 1 minus dn y of n minus capital N, that is equal to pk p0 xn p0 xn plus p1 xn minus 1 plus p m x of n minus m. And the reason this can be implemented is it's just basically you are just saying that your current output at time n, that is equal to your current input multiplied by p0 plus the previous input multiplied by p1 and so forth. So if you have saved the previous m samples of your inputs and the previous capital N samples of your output, you can just do the simple addition and multiplication to generate your output. Okay, so these are the IIR filters that can be implemented, and if you do the usual Z transform trick, what you find out is that implementable IIR filters are given by rational polynomials in Z, and that will be given by simply summation k equal to 0 to m pk z to the minus k, which comes from the fact that each time delay is nothing but multiplication in the z domain by z to the minus 1 or z to the minus 2 and so forth. So for example, if I took the z transform of this term, that will be pm z to the minus m x of z, and that's where this summation is coming from. And then you have summation k equal to 0 to dk z to the minus k with k. So I should actually have pluses here also. K equal to 0 to n, and that is coming. So the denominator polynomial is coming due to your previous samples of y. So for example, this is d of n z to the minus n y of z. So you know that we also had a question on that similar kind of a problem. You can verify that this is the form. If you have a system transfer function which is given by a rational function of two polynomials in Z like this, then we know that the numerator polynomial is of degree m, so it should have m roots. So it has m roots, and similarly denominator polynomial is of degree n, so it has n roots. Now, if assuming that there were no cancellation of factors in the numerator and the denominator, which means that the roots in the numerator don't coincide with the roots in the denominator, which is what in common terms you will call post-zero cancellation, then we know that the roots of the numerator polynomial, they correspond to zeros, and that means that we have m zeros and we have n poles, and this is the case that the n poles are for the case when they are not at z equal to 0. Okay, so not the trivial case of z equal to 0. Now you may have additional poles or zeros. So there are two cases, and you can find those cases by multiplying and dividing by z to the m and z to the n. So we did a very simple exercise of that in our practice problem, where we multiplied and divided by z squared, for example, in lecture 21, I believe. So here the cases you get is if n is bigger than m, then you also get n minus m zeros at z equal to 0, which means that if your degree of the denominator polynomial is bigger than the degree of the numerator polynomial, then you get some additional zeros. And if n is less than m, then this means that you get m minus n poles at z equal to 0. Okay, and this can be seen by multiplying and dividing h of z by z to the m and z to the n. So, and this is basically assuming that there are no pole zero cancellations. So a general IIR filter will have zeros, and it will have poles which are not at z equal to 0. That's the first thing. So we know this fact already, that an FIR filter only has poles at z equal to 0 or z equal to infinity, whereas an IIR filter, by definition, it must have poles other than z equal to 0. Okay, so this is sort of the breakdown that you get for an IIR filter in the z domain. If you do its pole zero plot, you should have m zeros and poles, and then at z equal to 0, you should get some additional either poles or zeros. Okay. Now, just like a causal FIR filter, we are also interested in only causal IIR filters. So causal IIR filter. Now, of course, in time domain, we know what a causal filter is. The definition of the time domain causality is the same for whether you have FIR or IIR, which is that h of n must be equal to 0 for all n less than 0. Intuitively, causality means that my current output does not depend upon future inputs. Now, the question is, what does, in terms of the Z transform, how can we figure out what is the causality? Okay. An IIR filter, basically, if it's causal, it looks like the following, that it is non-zero, it is 0 for all n before 0, and then it can be non-zero after n equal to -1. So let's say this is n equal to 0. And then, of course, it keeps on going, right? It does not stay 0 always. It always has some value. So h of n equal to 0.5 n u of n, for example, is an IIR filter. Now, these kinds of sequences, they are called right-handed sequences in the general terminology of Z transform, because they are 0 on the left side. If I put the sequence in front of me, they are 0 on the left side, and on the right side of me, the sequence keeps on going forever. So these kinds of sequences are called right-handed sequences. And these kinds of sequences have a very special property in terms of the region of convergence of Z transforms. So the property of a right-handed sequence is that the region of convergence always extends outwards from the rim of a circle. Okay, so a right-handed sequence region of convergence is always of the form that you have this some circle somewhere, it is not the unit circle, and the region of convergence is everything outside this circle. Okay, so this is the region of convergence for a right-handed sequence, and by definition for a left-handed sequence this will be inward towards the circle. Now where does this circle stand? Actually, the ROC is exterior to the circle going through the pole furthest from the origin. So if your IIR filter had basically, let's say, 4 poles, and 2 poles are here and 2 are here, these poles that are on the circle are the farthest away from the origin, and your region of convergence will basically extend outward from the circle that passes through those poles. Okay, so a causal IIR filter must have a region of convergence that extends outwards from a circle that passes through the pole which is farthest away from origin. Okay. Now the flip side of it is not true. If I give you just a region of convergence which has this, if I give you a Z transform which has this region of convergence, that does not imply it must be a causal IIR filter. Okay, because I can have a sequence which starts before n equal to 0. For example, a sequence which is 0 for all the points, but starts becoming non-zero at n equal to, let's say, -1. This sequence will also have a similar kind of an ROC. Okay, so an outward expanding ROC is a necessary condition for a causal IIR filter, but if I just tell you that an ROC has this form, you don't necessarily know that it is causal or not. However, if I give you an ROC which is like this, and it is an IIR filter, then you know for a fact that it is not causal. So an ROC which is going inward is always a non-causal IIR filter. Okay. So inward ROC is always a non-causal IR filter. Of course, this is, we are talking about the case of when you have poles. Because an FIR filter, the region of convergence of an FIR filter, it's the entire z-plane except z equal to 0. So if I exclude some parts of the z-plane, it cannot be an FIR filter. Okay? An FIR filter, the region of convergence is the entire z-plane, except possibly z equal to 0 or z equal to infinity. Okay, so that's just some information about a causal IIR filter in terms of the Z domain. Now, there is another aspect that we should understand, which is stable IIR filter. So the definition is a filter is bounded input, bounded output, stable if the following holds. If my input is bounded by some number b1, the b1 could be any number. If the absolute value of my input is bounded by some number, this means that the output value is always bounded by some finite number. Not the same number, b1 and b2 are different, but they are bounded. Okay? Where b1, b2 are finite numbers. Now, what does a stable system mean intuitively? What it means is that if I apply an input which is not infinite in magnitude, if the input is limited in quantity, it could be voltage, current, even some mechanical force, the stability extends to even the continuous time domains. Then there you will talk about the continuous time impulse response. If I apply some input, the output doesn't blow up. Right? So if you, for example, apply an input, some small voltage to a circuit that you have built, which is which acts like a linear time invariant circuit, you don't want the output voltage to just go unbounded. Right? So stability is a very important criteria that you desire in practical systems. Okay. Now, there is a very simple test for stability. The stability is, and this is a necessary and sufficient condition. So an IIR filter is stable if and only if we take our impulse response and we sum it from minus infinity to infinity, then that is less than infinity. Okay. The only way you can make your output blow up if your input is finite is if the total sum, absolute sum of your impulse response is infinity. In the continuous domain, the same condition is given through an integration. Okay. Now, stability we only worry about in the case of IIR filters. I have given you the definition, and from this definition it is easy to see that stability is only a problem in IIR filters. The question is why? So since FIR filters have only a finite number of coefficients, you can't add them, a finite number of coefficients, you can't add them up to get an infinite, to get some infinite number. Now, this is something that you have seen in your linear systems class. I'll just remind you. So what is a simple test? By looking at the pole zero diagram and telling whether your IIR filter is stable or not. you can simply look at the pole zero diagram and say that IIR filters are stable if and only if, and again, this is an if and only if statement. This is not like the causality statement, which is only necessary. If and only if all its poles are inside the unit circle. So just by looking at the pole zero diagram, you can tell whether the IIR filter is stable or unstable. So if you are given, this circle is now the unit circle. If you are given a diagram like this, you know that this is a stable IIR filter. On the other hand, if you are given a pole zero diagram like this, then this is for sure an unstable IIR filter. And a similar kind of statement holds for continuous time systems. I just want to remind you. Now, what is the equivalent of Z transform in continuous systems? That's the Laplace transform. Okay? And in the continuous systems, the condition that comes up is that if your poles are all in the left half plane, then you have a stable system. Whereas if any of the poles is in the right half plane, then you have an unstable system. So this discussion is once again the case where basically the Z transform gives you a lot of information that you don't really have to check. You don't have to go in and, for example, do the summation of your impulse response. Just look at the pole locations and you know whether you have a stable system or an unstable system. Now let's move on to the case which we did for the FIR filter design, which is what does the pole zero diagram tell us about the frequency response of IIR filters from the pole zero diagram. Now we already did that case for FIR filters, but in that case we only had zeros. In IIR filter now we have to ask what is the meaning of poles in relation to our frequency response. So we already know what the zeros do to the effects of zeros on the frequency response. What is the effect of zeros? They collectively bring down the magnitude of your filter around certain frequencies. Right? So it's given by the length of the distance from your zero location to the unit circle, and you basically just look at the length of that vector, and that is giving you the contribution of that zero to the magnitude response. Okay. Now let's look at what happens in the case of zeros, or when you have in the case of poles, or when you have both poles and zeros. So in that case, a general form of your frequency response is given by this: P0 over D0 e to the j omega n minus m, and then your response is given by basically each zero contributes to some response in the numerator. So you have e to the j omega minus zeta k, where this is the location of your zero. Okay. We already had this expression for the case of FIR filters. Now for IIR filters, we get another denominator factor which is due to the poles, e to the j omega minus lambda k, where lambda k is our poles. So this, you should really think of it as a vector going to frequency omega. So let me just remind you, this is your unit circle. Right? So let's say you are interested in figuring out what is the effect on this frequency omega. So this point in the z plane is e to the j omega. This is your point e to the j omega, which is the frequency, which corresponds to frequency omega. Now, if you have a 0 here, if this is your 0 location, let's call it zeta 0 or zeta 1. Then what is this vector? This vector is simply e to the j omega. So this vector is e to the j omega minus zeta 1. That is what this entire term is talking about. This term is simply the vector that is going from your 0 location to the frequency you are interested in. Okay. Now, what if I had a pole at this location? Well, again, this is my pole location. Let's call it lambda 1. Then this vector is simply e to the j omega minus lambda 1. Okay. So that is what this term is. This is simply measuring the vector. This is simply giving you the vector that starts from your location of the pole and ends at the frequency you are interested in. Okay. Now, understanding the phase is a little difficult in this case, but I'll just give you some intuition for the magnitude response of the IIR filter in terms of the poles and 0 locations. So the magnitude response is given by h of e to the j omega absolute value, that is p0 over d0, absolute value, summation k from 1 to m, absolute value of e to the j omega minus zeta k over summation k from 1 to n, absolute value of e to the j omega minus lambda k. So what this is saying is that every 0 is contributing, so you get a contribution which is proportional to the length of the difference from that 0 location to the frequency. Whereas poles, they basically appear in the denominator. So you are looking at 1 over the length of this vector. Okay. So I'll just take the example of one pole because we already have seen what the zeros do. To help you understand, of course, this one pole is going to result in an impulse response with complex coefficients, but let's ignore that for the time being. So if I have a pole here, and this is my frequency I'm interested in, my magnitude at this frequency is proportional to 1 over the length of this vector. Now, as the pole gets closer to the unit circle, as the pole gets closer to this point omega, what is happening to the length of the vector? It is getting smaller. Right? So what does that mean in terms of 1 over the length? That is becoming bigger. If a pole was on the unit circle, then the length of that vector is 0. And 1 over the length will be infinity. Right? So you don't want the pole on the unit circle because that will just blow up the magnitude at that frequency. Now, the farther your pole is from the unit circle, the bigger the length of that vector, and that means 1 over the length is getting smaller. So zeros, basically, if you want to intuitively think of it, zeros, as they get closer to the unit circle, they pull down the magnitude of your frequency response. Poles, when they get close to the unit circle, they are pulling up the magnitude. So they have the opposite effect of what zeros do. You move the zeros far away from the unit circle, your response is not getting pulled down much. And similarly, if you move the poles far away from the unit circle, your magnitude is not getting pulled up too much. Okay? So poles and zeros, that's effectively what they are doing. Zeros are pulling down the magnitude and poles are pulling up the magnitude. You want to stay away from very close to zero, or if you you want to stay away from the unit circle. If you get on the unit circle, then that means your magnitude is just going to blow up. Okay, so I'm going to just show you the same kind of effect that we saw by moving around the zeros earlier for FIR filter. We are going to just work with an IIR filter with an order 2. And this is the response that I get. This is the pole 0 diagram. Let's go back to the response and let's go back to the editor. So right now, this is where the poles are. And I'm going to start moving the poles. And you should, as we talked about, as I take the poles closer to the unit circles, the frequencies around that region are going to start, their magnitude is going to start going up. So I'll take these closer to the unit circle, and you see that you have now gone above the 0 dB, and this thing is sort of rising up. I keep on going, and there is really a bump appearing here. Right? So now I want to do minute changes. I'll do 0.99, and it keeps on going up. I do 0.999, and it's going higher and higher and higher around that frequency. Okay, I start making this smaller, and this will start getting pulled down. Okay, so now when you have many poles and many zeros, they interact with each other according to the equation that I wrote, but the general principle stays the same, what I talked about, that the far away a zero is, the farther it is for you the far away a zero is from the unit circle, the less effect it will have in terms of pulling the magnitude down. And similarly, the far away a pole is, the less effect it will have in pulling the magnitude up. Okay, and basically by doing the poles and zero placement, you can do a really good job of getting a really nice filter with the desired frequency response. Okay, one thing that you don't encounter in FIR filters, but you need to know about IIR filters is something called an all-pass IIR filter. So this is another type of filter that plays a special role in the IIR filter domain. And in general, an all-pass filter is the following. If h of e to the j omega absolute squared is equal to 1 for all omega, then hn is called an all-pass IIR filter. What this means is that the filter magnitude is simply a flat line. So h of e to the j omega magnitude is a flat line. And it's called all pass, as the name implies, because it just lets all the frequencies pass through the filter without any attenuation or any amplification. So what is this filter doing then? This filter is actually not changing the magnitude, but it is changing the phase of your input signal. Okay. So the role of an all-pass IR filter is simply to change the phase of the input signal. Now, because of the characteristics that we are interested in, an all-pass filter has a very particular form of its Z transform. An all-pass filter with real coefficients has the Z transform which is given by the following: h of Z equals, it's either plus or minus Z to the minus M dm of Z inverse over dm of Z. So the numerator and denominator polynomials in Z in the Z transform of an all-pass filter are exactly the same. The only difference is that one is a function of Z and the other is a function of Z to the minus 1. This dm of Z is defined as 1 plus d1 Z inverse plus d capital M Z to the minus M. Okay. Now, by looking at, so you can do the evaluation of this Z transform or try to come to the condition. I'll give you the condition directly. By looking at the pole zero diagram, just like, for example, the case of linear phase FIR filters, we looked at, they must have a special structure of their zeros to ensure that they are linear phase. Similarly, an all-pass IR filter must have a special structure of their poles and zeros to ensure that it is an all-pass filter. Okay? And in general, we already talked about the magnitude response. Right? We said the zeros are pulling down the magnitude and the poles are pulling up the magnitude. So if we were to think about that, what does this mean in terms of your IIR filter? Somehow, if you want your magnitude to stay constant, the poles and the zeros should somehow balance each other's effect, right? The poles and the zeros have to, the poles are trying to pull the magnitude up, the zeros are trying to pull the magnitude down. They have to somehow be in equilibrium with each other so that the magnitude stays constant. So that gives you a certain condition on the poles and zeros location, and the condition is the following: if Z equal to R e to the j phi is a pole, then Z equal to 1 over R e to the j phi, which means 1 over R e to the minus j phi must be a 0. Okay. This is the condition for an all-pass filter. This is how it will balance each other out, the poles and zeros. If you have a pole at a distance R, the zero must be at a distance 1 over R. If the pole angle is e to the j phi, the zero's angle must be e to the minus j phi. So if I have a pole zero diagram and I plot a pole here which is at distance R, so of course my pole, I'm only concerned with stable filters, so my R of this pole is less than 1. So what is 1 over R? It is of course greater than 1. Right? So my 0 is, that means is outside the unit circle. And if the angle of this is phi, then my 0's angle must be minus phi. So I get a 0 here. So I have a pole here, and correspondingly I have a 0 at the negative angle at a distance 1 over r. That's the condition for all paths. We are also interested in real coefficients. And we have talked about it many times. Real coefficients means that the roots of the polynomial must occur in, so they must occur in conjugate pair, which means that if I have a 0 here, I must have a 0 in it at its conjugation, which is exactly here. Okay. But if I have a 0 here, to make it all pass, I then must have a pole here, which also satisfies the conjugation condition. So in all pass filter, if I give you one pole or 0, you should be able to determine two other poles or zeros and one other pole or 0, whatever is left. Okay. And by the structure, basically what is happening is that the poles and zeros are canceling each other out in terms of the magnitude. The phase is still there. Okay. So an all pass filter, this is the condition, and for real coefficients, poles and zeros also occur in conjugate pair. Okay. So this is another case where you can just look at the pole zero diagram and tell what kind of a filter it is. If you see something like this, you know for a fact that it's an all-pass IIR filter. Now the question is, why would we be interested in an all-pass IIR filter? Why would we just want to change the phase? Or where are all-pass IIR filters used? So to answer this question, we need to know an important fact about IIR filters in general. Causal, let's add stability to stable, IIR filters cannot have linear phase. Okay. We already talked about the importance of linear phase, at least in some applications, especially speech or related applications. Causal stable IIR filters cannot be designed to have linear phase. They never have linear phase, which means their group delay is not constant. So if you have an IIR filter, let's say you have a filter, let's call its impulse, its Z transform H1Z, you input Xn, you get output Yn, the phase of Yn has been distorted. So one way is that you stick an all-pass filter after this H2Z, which is an all-pass IIR filter, to get Y tilde N, which tries to invert the non-linearity of the phase of the first filter. So if your first filter had a, for example, group delay, if this had a group delay, let's say of this form, then you try to invert that by designing the group delay of this so that together their phases cancel out each other, and at the end of the day, their combination, you get simply a constant group delay. Okay. So when you put two filters in cascade, their magnitudes gets multiplied, right? But their phases get added. So you can try to invert this phase distortion or nonlinearity. And that's where all pass filters are used. They are always used in applications where you are trying to manipulate the nonlinearities caused by your circuitry or other filters to correct the phases. Okay? Because in some applications, having the right phase is very important. In other applications, it may not be that important. So again, if you go to the FDA tool, you go to IIR filter, and then under this basically radio button, you have a option called arbitrary group delay, okay, which is effectively an all-pass filter. You can, it is a computational method which lets you design a filter which has an arbitrary kind of a group delay. You tell us from this to this end, I want, so it takes inputs of frequency vectors. So you divide your 0 to pi region into different blocks. So in this case, you are dividing it from 0 to 0.1 pi to pi. So this is what you want your group delay to look like. You want to go from 0 to pi, and this is the group delay vector that you want. 2, 3, 1. This is relative. Okay? The group delay can start at any point, but what you want is that by the time it reaches the next point, it gains a value of 3 in the group delay. Right? And then when it reaches the next one, it has come down to 1. So it starts from 2 and it goes up to 3. So there should be basically a relative difference of group delay of about 1. And then it goes from 3 and it has to come down to 1. So there is a relative reduction in group delay of -2. Okay. And the final thing, this weight vector is 1, 1, 1 here. This is basically a command for MATLAB because you don't have a closed form solution for this. MATLAB is trying to do an optimization algorithm. So what this 111 tells is that you really care about this group delay condition more than that. So if I make it, for example, 1011, this means that I want my first condition to always hold regardless of what happens to the other conditions. Okay? Because sometimes MATLAB may not be able to design a filter which you exactly wanted. The algorithm it uses is called the constant least pth norm. I'm not going to go into the details of that. Okay? Now, if I allow this, if I design the filter, you see that the magnitude is 0 dBs because we wanted it to be an all-pass filter, which means the magnitude stays at 1, which is 0 dBs. And if I go to the group delay, it's not going to look exactly like what you wanted, right? But it's about the same. It starts at 10 and it goes up to 11 around 0.1. Again, it's a computational, it's a numerical method. You're not going to exactly get what you desire. And it's not going to be just simple linear lines, but it tried to match your condition. It tried to go from 10 to 1. So you had go from 2 to 3. So you wanted a distance of 1. Right? You wanted a group delay to increase by 1 when you reach 0.1. And it has tried to do that. At 0.1, it is getting close to 11 because it started at 10. Now you want it at pi to reach back to 1, so you want a -2. You want a downward trend of -2 group delay. Okay? And so it has tried to go, it's not again a straight line, it has tried to go from 11 to 9. It can't exactly hit 9 because again it's a numerical method. It can't exactly give you what you desire. I could have changed it. I could have said I want 0.1, then let's say 5, and I want to go from 2 to 3, then I want to come from 3 to 2 at 0.5, and then I want to go to 1, and my weight vectors are all 1, 1. I do the design, and the method is taking its time. It may or may not be able to solve it. It is so this is what it gives me. It says computing response done. It changed a little bit because I said at 0.1 I want it to be around 2, so I wanted to lose 1 point. So around 0.5 it managed to do that. Let's go and make this 0.5 point as 1 and this as 0.5. Okay. Now you see that I wanted here to be around 1, so I wanted it to lose 2. So now it has changed the shape. It is gaining 1 in the group delay. At 0.5 it is losing again 2, and then rest it's trying to lose only 0.5 of the group delay. Okay. So it will roughly try to match whatever conditions you give it, but it's not going to exactly do what you want it to do. Okay, so we talked about the fact that IIR filters have these distortions. The question is then why use IIR filters? And the advantage of IIR filters is the following, that it gives you the same magnitude response as an FIR filter if you are not interested in phase that much. If you are doing speech applications, it's best to stick with FIR filters. But if you are not interested in phase that much, then you can have same magnitude response as an FIR filter, but with much smaller order of the filter. An order of the filter effectively translates into how many buffers you need to store the values, how many delay elements you need, or effectively how much computation time you need. So something that an FIR filter might be able to do by using a length or order of 150, an IIR filter might be able to do the same task by using just a length of order, a filter of order 15 or 20. It's a significant reduction. The disadvantage, of course, is what we talked about earlier. We cannot get linear phase. Now you can try to stick an all-pass filter after an IIR filter to get linear phase, but then you have to count the cost of both the filters. And if you stick an all-pass filter after an FIR filter and you count the total cost, then the savings in order are not that huge. You may be able to save on a few 5 or 10 or 15, but it's not that huge savings. So really the message is, if you want linear phase, stick with FIR filters. Okay? Unless you absolutely necessarily have to go to IIR for some reason. So we'll look at an example of these things to convince ourselves that indeed FIR filters require more higher order. So let's say we are interested in low pass filter. We are interested in the pass band to be at 0.2 pi and the stop band to be 0.3 pi. Now let's read the specifications here. And I have selected minimum order. So MATLAB will try to do its best to design an FIR filter which meets these specifications but has the smallest order possible. So let's do that. Let's do a design filter. and it gives me an order 50 filter. Right? If I, of course, make it more stringent, I say I want to go to 0.24, the order will, of course, go higher. It's now 127. Right? Now, the only thing I'm going to change is go to IIR. And right now, we haven't discussed it, but there are 4 more main types that you can try to use: Butterworth, Chebyshev 1, Chebyshev 2, or elliptic. So let's just use Butterworth, which is the simplest one. You are getting an FIR of order 127. Okay, so focus on this. The same specification, I have not changed anything. I just say design filter, and I get an IIR filter whose, of course, shape is different, but its order is now 51. So you got about more than half the reduction in complexity. What is the price you are paying? Let's go to the group delay. This is the group delay you are getting. You're not getting a linear phase. You're not getting a constant group delay. Okay? If that works, then you should use this IIR filter. Okay? I could actually reduce this order even more by selecting, for example, an elliptic filter, which we'll discuss in a little bit. And now you meet the same specifications with an order of only 9. You have gone from 127 for an FIR filter to an order 9 filter in IIR domain. Of course, the group delay is still pretty bad, okay, and it's even in a worse shape than the previous case. Now, the other thing I want to point out, I've been playing with this tool because it's really a useful tool, but one thing that you should really know about is that behind this tool are actually all MATLAB functions that if you ever want to implement, you should really learn how to code those MATLAB functions. Okay. For example, the arbitrary group delay knobs that I played with, behind that toolbox, it's really using this function called IIR group delay. If I take the help, it provides you all the help that is available about this IIR group delay, and you could call this function using the command line. Okay? I mean, it's much easier for me to show you the GUI, but if you want to implement something or calculate something more, you can also use this direct command line. So each one of the options that we have seen in the FDA tool has a corresponding function that actually the GUI is calling.